Welcome to Chapter 2, Relations and Functions. In this chapter, we'll learn how to connect pairs of objects from two sets, understand the concept of relations, and then explore functions, one of the most important concepts in mathematics. This work was pioneered by G.W. Leibniz in the 17th century. Let's start with ordered pairs. An ordered pair is simply two elements written in a specific order, like AB. The key point is that order matters. The pair AB is different from BA unless A equals B. Two ordered pairs are equal only when their corresponding elements are equal. The Cartesian product of two sets A and B, written as A cross B, is the set of all ordered pairs where the first element comes from A and the second from B. If set A has P elements and set B has Q elements, then A cross B will have P times Q elements. Note that A cross the empty set gives the empty set. Important properties of Cartesian products. First, A cross B is not equal to B cross A. The operation is not commutative. Second, A cross A gives ordered triplets of the form A, B, C. R cross R represents all points in a two-dimensional plane, while R cross R represents three-dimensional space. Let's see an example. If A equals 1, 2, and B equals 3, 4, then A cross B gives us four ordered pairs, 1, 3, 1, 4, 2, 3, and 2, 4. But B cross A gives 3, 1, 3, 2, 4, 1, and 4, 2. These are different sets, showing that order in Cartesian products really matters. Now let's understand what a relation is. A relation R from set A to set B is simply a subset of the Cartesian product A cross B. It describes a connection or relationship between elements. We can write it as R equals the set of ordered pairs x, y, where x is in A, y is in B, and x is related to y in some specific way. Every relation has three important components. The domain is the set of all first elements in the ordered pairs of the relation. The range is the set of all second elements. The codomain is the entire set B. Remember, the range is always a subset of the codomain. How many relations can exist between two sets? The total number of relations from A to B equals the number of possible subsets of A cross B. If A has P elements and B has Q elements, then A cross B has P times Q elements. The number of subsets, and hence relations, is 2 raised to the power PQ. Arrow diagrams are a great way to visualize relations. Draw two sets and use arrows to show which elements are related. The arrows point from elements in the domain to their images in the range. This makes it easy to identify the domain and range at a glance. Relations can be classified into different types. An empty relation has no elements related. A universal relation relates all elements. A reflexive relation has every element related to itself. We also have symmetric and transitive relations. We'll explore these properties in more detail in later chapters. Now we come to functions, a special and very important type of relation. A function from set A to set B is a relation where every element in A has exactly one image in B. No element can have two different images, and every element must have an image. We write this as f from A to B. Let's understand function notation. When we write f from A to B, it means f is a function with domain A and codomain B. If f of A equals B, we say B is the image of A, and A is the preimage of B. The set of all images forms the range, which is always a subset of the codomain. Real-valued functions are those whose range is either R or a subset of R. A real function has both its domain and range as subsets of real numbers. Most functions we study in school mathematics are real-valued functions. Their graphs can be drawn on a coordinate plane. The identity function is the simplest function, f of x equals x. Every element maps to itself. Both domain and range are all real numbers R. When you graph it, you get a straight line passing through the origin at a 45-degree angle to both axes. A constant function always gives the same output regardless of input. If f of x equals c, where c is some constant, then every input gives output c. The domain is all real numbers, but the range is just the single value c. The graph is a horizontal line at height c. Polynomial functions are functions like f of x equals a0 plus a1 times x plus a2 times x squared, and so on, up to n times x to the power n. Here n must be a non-negative integer. Examples include f of x equals x squared minus x plus 2, or g of x equals x cubed. All polynomial functions have domain equal to all real numbers. Rational functions are ratios of two polynomials, f of x equals p of x divided by q of x. The key thing to remember is that the domain excludes any value where the denominator q of x equals 0. For example, f of x equals 1 over x has domain all real numbers except 0. The graph often has vertical asymptotes. The modulus function, also called absolute value, is written f of x equals the absolute value of x. For non-negative x, it equals x. For negative x, it equals negative x. The domain is all real numbers, and the range is all non-negative real numbers. The graph is V-shaped and symmetric about the y-axis. The signum function tells you the sign of a number. It returns 1 if x is positive, 0 if x is 0, and negative 1 if x is negative. The domain is all real numbers, but the range is just 3 values, negative 1, 0, and 1. It's useful for determining the sign of any real number. The greatest integer function, also called the floor function, is written f of x equals square brackets around x. It returns the greatest integer less than or equal to x. For example, the greatest integer less than 3.7 is 3. For negative 2.3, it's negative 3. The graph looks like a series of steps. Now let's learn about the algebra of functions. We can add two functions, f plus g of x equals f of x plus g of x. Both functions must have the same domain, or at least overlapping domains. The domain of the sum is the intersection of the individual domains. For example, if f of x equals x squared and g of x equals 2x, then f plus g of x equals x squared plus 2x. Subtraction works similarly. F minus g of x equals f of x minus g of x. The domain is the intersection of the individual domains. Remember that order matters here. F minus g is not the same as g minus f. The difference changes sign when you reverse the order. For multiplication, we have f times g of x equals f of x times g of x. We can also multiply a function by a scalar, k times f of x equals k times f of x, where k is any real number. The domain is again the intersection of domains. This is called pointwise multiplication. Division of functions is f divided by g of x equals f of x divided by g of x. But there's an important condition: g of x must not equal 0. So we must exclude any points where the denominator function equals 0. The domain is the intersection of domains minus all points where g of x is 0. Let's summarize Chapter 2. We learned about ordered pairs and Cartesian products, the foundation of relations. Relations are subsets of Cartesian products that connect elements between sets. Functions are special relations where each element has exactly one image. We studied various function types: identity, polynomial, rational, modulus, signum, and greatest integer functions. Finally, we learned how to add, subtract, multiply, and divide functions. Thank you for joining Chapter 2 on Relations and Functions.